So knowing what we knew from one dimensions, how would we find local maxima and local minima for two-dimensional functions? So consider this function. So here I'm plotting x and y, and this creates this xy plane. And then in the z-axis, I'm plotting f of xy, as usual, yeah? So then, clearly this is a local maximum. Well, this is a local minimum. So what do maxima and minima have in common? So what happens is that at the maxima and at the minima, the tangent plane is exactly flat, exactly horizontal, okay? So this means that the slopes in both the x and the y direction must be equal to 0, okay? So that happens for stationary points. Beware that it will also happen for this third type of point called a saddle point, which is a special case of stationary point. But we can conclude that when the partial derivative of f with respect to x and the partial derivative of f with respect to y are both equal to 0, then this is a stationary point, okay? Another way of saying this is to say that the total differential df is equal to 0, okay? Because remember the definition of total differential. If the two partial derivatives are 0, then df is 0, okay? So we can write that df is 0 is also the same condition. So this means that this will be a stationary point. Okay, so a stationary point. So by solving these two equations, the partial with respect to x equals 0 and the partial with respect to y equals 0, this will be two equations. It's a system of two equations. We solve for x and y, and that will give us the xy coordinates of the stationary points, such as maxima, minima, and saddle points, okay? Next, we are going to study how to classify them. See you in the next video.